So now we're going to look at a different library, this pandas library, for processing heterogeneous data. In the morning we saw NumPy, which is good for dealing with numeric data, if you have tables of numbers or vectors, something like that. Sometimes we also have other types of data, like names, addresses, categories, and we can have everything mixed up in tables. And this pandas is a very useful library for dealing with that kind of data. So pandas is built over NumPy, and it has similar properties like broadcasting and the kind of indexing we can do, but it has two very important objects that you can create from these classes, series and data frame, that make it very easy to deal with data that has indices and that can have different types of values in the same table. So basically a series is a vector of values, an ordered set of values that also includes an index. We can create a series object using this series class. These classes, I'm going to talk a bit about classes in next week, but by convention in Python the name of the class is written with an uppercase, the first letter. And the class is a generator for objects. It produces an object, in this case a series type object, and we give this class the values that we want in the series, and also optionally we can give an index. So in this case we have these values, 4, 7, etc., and they are assigned an index here, which we can use to fetch its value or to refer to each value. We can also create a series from a dictionary where the keys will be the index and the values will be the values for the series. We can use broadcasting exactly as we did in NumPy. For instance, we can ask for compare all the elements in the series with 12, and we obtain also an ordered array of true and false. Only in this case, this is also a series and has the same index as the original one. So we know that element A is not greater than 12, element B is greater than 12, and so on. We can use these indexes to access each element. For instance, the value of element A is 12. It works in a way similar to a dictionary in this sense, only it does not have that restriction that keys cannot be repeated. So for a series, you can have repeated values in the index, and in that case you will get all the values associated with each index value. We can also index the series with series of booleans, or arrays of booleans, or series of booleans. If we use a series of booleans, the series will use the indexes to match the values. If it's simply an array with the same length, we have it will do it by order, so by the order they come up in the series. So in this case we can retrieve from our series all elements that are greater than 12, and we obtain just part of the series with these elements, or we can actually keep these. Sometimes it's useful if we have some conditions that we want to reuse, we can keep these conditions in a variable, because the result of this operation is also a series with these true and false, so we can store that in a variable and we reuse. In this case we create a math variable which has this series, and then we can use that to index the other series and obtain the values from those indexes. Another important class here in pandas is the data frame, which is basically a table. It has columns and rows, and the columns have these headers. For instance, we can create a data frame with a dictionary where the keys are the names of the columns and the values are the values that we put in the column. So associated with each column we put in a list with all the values for that column, and this defines a table. This table can have mixed types of values. So here we have numerical values, here we have strings, so we can mix them together and we can have heterogeneous data in the same table. We can access data in the table by, for instance, the column. So if we use the name of this data frame, this table, and then we access the name of the column, we obtain a series with the data in that column. We can also manipulate the data frame, the table there. For instance, we can drop columns using this drop method. There are different methods that you can use. So I'm going to show some examples, but in this case we are dropping this in the using the name of the column, and we are dropping one column. So we are removing one part in this axis one in the column direction. So this function will return a new data frame with only the remaining columns. We can also drop rows. For instance, we are going to drop the third row, or the one with index 2 in this case, since the index is starting at 0. We're going to drop this row along the, so we are dropping one row. This is the axis 0, the row axis, and we drop the whole row, so we get returned from this function the original table, but with the row with index 2 missing. So we can manipulate the data like this, and we can do more complex queries. If we index with one name, so using the data frame and then putting in one name, the data frame object will assume this is the column and look for a column with that name. We can also index the row with this IX field, and we can index this also with booleans, like we did with NumPy table. So if we want all the stars that are at greater than 100 light years distance, we can say that from the stars we want all the rows which have true in this condition, and the condition is the distance of the star, so this column is greater than 100, and this returns the rows corresponding to that condition. So this way it's easy, if you're dealing with large tables, to extract the information that you want, filter data from the tables, and so on. There are many different ways of using these objects, and they have many different functions. The Pandas library is quite extensive. I'm only going to show a few examples, but here there are basically two possibilities. Most of you probably will only be dealing with numerical data, so the idea is just to know that this exists in case you need to deal with this sort of data. Some of you will perhaps be dealing with categorical data and may have to do this sort of manipulation. In that case, this will be the starting point for you to look into the documentation in more detail, and the book I recommend covers this quite extensively, so you have lots of examples of using pandas with that book. I'm going to give two examples. The first one, we're going to process data on public spending from this site, bars.gov. These data can be downloaded in CSV files, but the site only allows us to download 2,000 records at a time. So I'm going to show an example of what I did downloading the records starting from January the 1st, 2015, and then records starting from January 20th. There is some overlap between this file and the other one with the 2,000 records limit, but this way we can get a larger span of time. Of course, we could do this with more steps, but two of them are just to illustrate how we can do this kind of solve this kind of problem. And then we need to merge the two together and remove whatever is repeated there. So this is the kind of files we have there. There are the kind of contract, the amount on the contract, dates, and things like that. So we have text data, we have numerical data that's actually strings with these euro signs, and so we have a lot of mixed stuff here in the data set. We're going to use this read CSV function from the Pandas library, which returns the data frame with the data on the CSV. So we can read both tables. We have the first table and the second table. We just need to use the read CSV function and give the separator if it's not the default, which is usually a comma. In this case, it's a semicolon, so I tell the function that this is a separator. And this will automatically identify the strings and the numbers and convert the data, and so I can see which which columns I have, and I have here the list of columns. And now here, this is also, I chose a data set in Portuguese because this is a problem that you may eventually have. The details may be a bit complex and vary from case to case, but the problem is that we are not dealing with only ASCII characters, the standard character set. So these are actually Unicode strings. You can see when Python displays them, it puts a small u before the string. So this is not a byte code string, it's not the actual bytes, but they are represented in Unicode, so it can represent all those extended characters. Also, when you need to include those characters in your source code, you need to have this directive at the beginning, coding UTF-8, and save the file in UTF-8 coding. This is so the interpreter knows the file is in that format. You don't have to worry about this with Spyder because every time you create a new file for Python in Spyder, it puts this automatically. But if you're working with a different editor, you probably need to remember this. So sometimes we have lots of problems with the way you have encoding, because if you read one file in ANSI and another in UTF-8 or something like that, and the encodings are different, you have to convert the strings. So I'm not going to talk about those things in detail, but there may be some problems when you're dealing with text with strange characters, either in Portuguese or other language, any other language that's not strictly the basic character set for English. So in this case we have these columns, they are all Unicode strings, and we can concatenate the two tables with this concat function from Pandas. So I imported the Pandas library as PD, and also imported directly the series and data frame classes. This is, it seems redundant because I'm importing Pandas twice, but since these two we often use a lot to create new tables, new series, and so on, it's often useful to include that import specifically, so we don't have to include the PD on all of that. And then if we need to use other functions sometimes, then we can also import a module. Or if you prefer, you can just import a module and prefix the PD on everything. So this is just an example of why we may want to do the two imports. So now we concatenate the two tables. We have here so we have these two tables, and we call the concatenate function, and it will just put the two tables together into a single table. Of course, since they have some overlap, there are repeated values here, and we'll have to deal with those. So we can call this from the table that we have, the result of concatenating the other two, so the total table. We can call this duplicated method that gives us a series with true or false to indicate whether or not a record there is repeated before it. So the first time it encounters a set of values, that one is not repeated, but if it encounters exactly the same values again, then that one is flagged as repeated. And we can call, now we have this duplicate, which is a series from the original table. It's a series of true and false. And we can ask for this. This is an example of a useful method in series, which is value count. It returns a series with all the different values we have there and how many times they occur. So basically duplicated, there are 3,632 false and then 368 true. So these 368 records are duplicates of records that also appear before on the table because of the overlap between the two tables. An alternative is we can use value count and then access the true by the index and see how many of those are true. So removing duplicates is very easy because we have this method there, drop duplicates. This is a very common problem with tables. So there is a method just for that. It says drop duplicate and it returns a table without the duplicates. That's why I'm putting it back on table. So if I just do drop duplicates, the original table is not changed. But this way I copy everything else and put it again on the same table. So this way I change the table. Now there is another problem, because since when we load the CSV file we did not specify an index, the read CSV function created an index each time we loaded the CSV file. So since we loaded two of them, the indexes were created from 0, and now we have different records that share the same index because they were loaded in two different files. So we need also to fix that. We want a unique index for our records. So we call reset index, and the data frame will rebuild an index starting from 0. So this is just to show some common functionalities. Basically, we loaded two tables that have some overlap. We dropped the duplicates, and now we fix the index so that it starts from 0 onwards, and every record has its own index value. So now let's look at how we can use the data. We see that the price of each contract is stored as a string that has the period marker to indicate thousands, and then has a comma for the decimal part, and then has a space and the euro sign. And so I don't know if this was done deliberately, but we cannot use these as numbers easily because they are all mixed in with all these signs. So if we want to look at the values, we need to convert these into numbers in euros, and we need to clean this field. So basically, this is what we can do here. From our table, we create a copy of the series, contratual. The reason for creating a copy is that when you access a series, this is optimized for large data sets. So usually what you have is a view on that part of the table. So if you do something in the series, it can affect the original table. This is optimized inside the way the code was written for pandas, but usually with very large tables that is a desired behavior because we don't want to copy the data unnecessarily. But this means that you also get warnings when you start trying to alter the data, warnings whether or not you have a copy or you're looking at the original data, because this depends on some optimization, some assumptions the object is doing. So if we explicitly say we want a copy, there will be no warnings of, like that, and we know that we are working with a copy of this data, so there is no problem. We know we are not changing the original data. So now, for each value in the index of this series, I'm going to obtain the value of this series there, so each of these strings. I'm going to split it on the space and keep only the first part. So splitting on the space will split these two bits, and I only want the part with the numbers. So on variable s, I will have the part with all the numbers without the euro sign and all those things. And then I will replace every dot with an empty string, so this will remove the dots from each of these strings. And then I will replace the comma with a dot, because the decimal marker in Python is the dot, not the comma. And then I will copy I will put the string again in the series. So I fetched this string from the series, I cleaned the string and put it back in. I'm going to do this for all of them to remove those signs.
I didn't quite get why this is 0, because I had the same problem with an exercise. What does the 0 mean?
The split?
Yeah.
Zero.
Yeah.
Split creates a list with the parts of the string. So if we split on the space, we will have a list with this part first and then that part. The first element of the list is index 0. So if we want only to keep this part with a number, we only need the first element of the list. Okay? So we are basically throwing away everything after the space that may appear there. Then we replace the markers here, we delete the dots, and we replace the columns. Yes, just because it's in the wrong format for conversion. And we do this for all those in the series. So this is a loop for all the values in the index, and we do this. We clean it and we put it back into the series. After this, we're going to put in our table the series already cleaned up, but we're going to change the type to float, because these so far are all strings. We're going to change them to float with the numbers with those decimal parts, and we'll put them again in the same place on the table. So now we have in our table, if we look for the values in the column, now we have real values instead of those strings that we had originally. So now we can use these functions that we have in the data frame object, so these methods like maximum, the average, the minimum, median, and so on. We can ask for all these values. We can see, for example, that the minimum price of contract is 0, which seems a bit strange, a €0 contract. So we can actually take a look and see which of those contracts have 0 value. So we can create this mask, which is a series of true and false for this condition, which is the price is equal to 0. So we get, this is a series from the table. This column is a series of values with the index and the values. Comparing this to 0 gives us a series with the same index but true or false values depending on the comparison. And now we can even do something like this. This seems a bit strange, but when we are summing or doing these numerical operations, false counts as 0 and true counts as 1. So a simple way of counting how many truths we have is simply to sum all the values here. So all the false will count as 0, and we get 9, which means that there are 9 records in our table for which that condition is true. And now we can ask from the table the records that comply with this mask. Now this can be a bit confusing at first, but these objects are relatively smart. Usually when I index a table, I'm giving the name of a column. So this is the standard thing, for instance, like this. But if I give an array of booleans that is the same size as the number of rows, the object knows that I'm referring to the rows and not to the columns. So in this case, this works. Usually you may want to use IX explicitly so that it's easier to understand when looking at the code, but you can also do it like this. As long as it doesn't create too much confusion for the object, it works well. So in this case, I'm asking from the table all the lines that have a true value in this mask. And this lists all those contracts which have no euros, so 0 euro in value. Now we can do different things. For instance, we have the cumulative sum too on this series. So we can ask, we can put here in the price series the column with the price of the contract. The total cost will be the total cost up to some contract. So we are drawing the cumulative sum of all the values, and then we can plot it. In Pandas, the series themselves have wrapper functions for plotting. So we don't actually need to import matplotlib and then plot the data on the series. We can just run the plot function from the series object. So this is simple. If you want to just check, look at some data quickly, it makes it much easier. And then I just save the figure and close. So if I want to do this, I want to save the plot, I need to import it from matplotlib. But if I just want to look at the plot, I can use Pandas for that. So this would be the cumulative sum of all the contracts. So we are adding the cost of all the contracts and so on. And then we can do histograms. For instance, we can select all those contracts with more than 50,000 euros in price, and then do the histogram of those values. So in this case, I'm creating a mask with true and false, depending on whether the price is greater than 50,000. And then I'm selecting from the table all those rows which have over 50,000 price in the contract, and I'm plotting a histogram with 50 beans for the series corresponding to the contract price. So looking at these expensive contracts, looking at the column with the price, I want a histogram with 50 beans, and I have this histogram here. And I can do the same for the less expensive ones. I should have used a different name here, but I can ask for those below 50,000 and do the histogram again, and so I get this one here. So this Pandas gives us very quick access to this sort of functions that make it simple to visualize the data and to examine the data that we have, and also to build reports and so on. So you don't need much code to work with complex data like this. Just to give another example, we have this database of nearby stars. This catalog has about 12,000 or something like that, and it has things like the absolute magnitude, the apparent magnitude, the distance, the spectral type of the star, and so on. So again, it's a mixed type of data. Many of the fields are numeric, some of them, like the spectral type, are strings, and we can use again Pandas, the read CSV, and load all the data in the table. And now this is just to show a few other things. Remember the value count method. This counts how many times each value on the series occurs and returns the series with those counts. And it sorts them by frequency. So the most common one is first, the second most common one is second, and so forth. So if you want to keep or know which are the 5 most common spectral types, we only need one line of code. So this is the series with the count for the 5 most common ones. We get from our star data, the whole table, the series for the spectral types, and for that series we ask for the value count. So this counts all of the spectral types. But since we want only the 5 most common, then we select only the first 5 of those series, of that series. And this is a series that indicates for each spectral type how many times they occur, and it's sorted by frequency. So now we can do a histogram, for example, of the magnitude of the most common spectral type, that's K0. We fetch the most common type from our count here. So the one that comes first with index 0, so the first index will be the spectral type of the most common spectral type that we have in our data. So this works regardless of what values we have here. And it's a good practice to do that. It's not a good idea to look here, see it's K0, and then fix that in the rest of our script, because if the data changes, then the rest doesn't change. It's best if we store this in a series and then just pick the first one on the series, because the series is ordered and we know the first one will be the most common one. So this is, of the index of the series, the first element. The index of the series is this part here. The first element will be the most common spectral type. And now we get the absolute magnitude from our table for those stars which have the spectral type equal to the most common type that we found. So we are selecting only the stars of the, in this case, K0 spectral type, but if the data were different, then it would be another most common spectral type, and we get this series. So this is a series because we are only looking at one column, the absolute magnitude, and it's only a subset of the stars because of this series we only want those for which this is true, those stars for which this is true. So we are looking at a series with the absolute magnitude of all stars of spectral type K0. And now we take that series and plot the histogram and save the image. So this would be a rather complex query to do if we had to look through the table and select everything and count everything, but we have all this already implemented in Pandas. So it's easy to just call the right method and get the result. Now we can do something a bit better. Histograms are not very good because they have these fixed bins and then they count the occurrences in each bin. And slight changes in the data or in the position of the bin can make the histogram look quite different. So we can smooth this out with kernel density estimation. The idea here is that we use the kernel function, which is a continuous symmetrical function that has an integral of 1. It can be whatever we want. It can be triangles, Gaussian, cosine, something like that. But the important thing is that it is symmetrical. Or we can center it on a point and it will be the same for both sides. And the integral is 1. So that each time we add this function, we add an area of 1 to our graph. And now what we're going to do is for each point, instead of merely counting the number of points in each beam, we're going to add one of these kernel functions centered on each point that we have. So on each absolute magnitude, we would add a little Gaussian here. I'm going to use the Gaussian kernel density estimator, and then add another one and another one and so on, and then we have something smoother with showing the distribution. So this would be the result. Instead of having this jagged histogram, we would have this smooth line because we are adding a small Gaussian curve for each magnitude that we find. So in those places we find a greater number of magnitudes, we have a higher peak. Where it's smaller, we have a smaller value. And this is easy to do. We're going to use SciPy again. We're going to import the Gaussian kernel density estimator. So this is a function that does this. Actually, this function allows us to control the width of the Gaussian and so on, but we are not going to worry about that. We're going to use the default. And this is how to plot the kernel density estimation. We have the data here, which is simply the set of points that we want to plot in our chart. And we are going to plot the graph in a number of steps. So these steps do not affect the actual kernel density estimation. It's just the smoothness of the plot, because when we plot, we are joining points with straight lines. If we keep those points too far apart, then we see the jagged lines on the plot. In this case, we're going to try to smooth it a bit, so we're going to use more steps. But the shape of the values of the points will always be the same with kernel density estimation, unlike what happens with histograms, which can change when we change the beam. So we're going to get the range of the data. The minimum and the maximum will tell us when to start and stop the plot. We're going to build a range of values for the axis. This I could use linspace. I'm just going to show a different function. This A range. We give the minimum, the maximum, and then we give the step size, so we can have a range of values that are not integer. And the step size is merely the difference between the maximum and the minimum divided by the number of steps that we want. So this gives us a set of points where to draw the graph. We compute the kernel density estimation for our data, and then we ask this object, this KDE object, which is the result of the Gaussian kernel density estimation function, we ask to compute the epsilon values corresponding to the x values where we want to plot the graph. And now we return this pair of vectors which have the x values and the y values. So we can look through all the 5 top spectral types and plot their absolute magnitude distributions using kernel density estimation. So we select the top 5 indexes from our count series. Since that one is ordered by frequency, we get the most common one. And for each of these spectral types, we're going to select the data from our table. We're going to print the mean there, just to see it on the console. But then we're going to obtain the kernel density estimation with 100 points for the plot, so the plot is smooth. And we're going to plot it on our chart. And since we are doing this for all these 5 most common, we get the 5 lines, and then we insert into the plot a legend with these selected strings. So the spectral types we selected are 5 different strings with the different spectral types, and this will be the legend. Since the order is the same, the legend labels will correspond to the series we plotted. And then we just save the figure. So we obtain these results here, showing the different distributions on the absolute magnitude for the most common, the 5 most common speckle types. So basically, this is now a significant change in the way we're going to proceed with the course, because up to this morning was basically those things that all of you most likely needed to learn to process data. So the basics of Python, plotting, and dealing with numerical data. Because even if you're dealing with categorical data, eventually you have statistics and so on, you need to do plots, so you need to also to be able to work with vectors and those kinds of things. From this point onwards, I'm going to start talking about things that may be useful in some cases, but probably not in other cases. So now it's so we can also dedicate more time to your final project, and you should now pick and choose which things are more interesting for your work. You don't have to learn all of these, although it may be useful just to remember that it exists, because if someday you need to use it, then you already know where to look for the documentation and how to use it. Okay? So basically, the Pandas library is the main subject of the book, so you have lots of examples there on the book. You also have online, you have lots of tutorials on Pandas and extensive documentation. If you ever need to work with tables in this sort of way, where you have to select data and filter out data, clean the tables and so on, this is very useful for that kind of work. And now for the part of the assignment, you have a simple exercise, which is basically starting from the star kernel density estimation. You change it a little and work with that. And from now on, we'll have more time available for your final project. So it will be nice if you send me some emails with your plans, or we could discuss it here too, so that next Saturday I could talk a bit more specifically about the kind of things that you want to do. If I don't have any details about what you want to do, I can give other examples, but maybe they won't be as relevant, okay?